Yes, class, am I audible to you? Alan, Farhat, Hanifa, Hiba, Memuna, Saifullah.
Yes, ma'am.
All right. Okay, sir, class. So see, we'll start with work energy in part. So what we'll do, whatever formula based things are there, I'll give you sufficient time so that you can write down the formula at least. Then afterwards, after this formula part, we'll then jump on to the numericals. Now see, what is work done? First, we'll cover work. It's the dot product of force and displacement. All right. Now, if suppose a body is there and a force has been applied at a certain angle and the distance displacement has been covered by the body, then the dot product of the work done and the displacement, this gives us the quantity which we call as the work done. So work done's formula is F dot S, or we write it as Fs cos theta. Because dot product is there, so we'll write it as Fs cos theta. It's a scalar quantity. SI unit is joule and CGS unit is earth. Now 1 joule is equal to 10 to the power 7 earth. This is the conversion. Joule is the SI unit, earth is the CGS unit. So if you have to convert joule into erg or erg into joules, you can use this relation. 1 joule is equal to 10 to the power 7 earth. Just note down this page.
Done, sir. Done now.
All right. Now, so basic formulas are there. Yes, graphical method is there. So if you have force versus displacement graph, then you just have to take the area, whatever is the area under the graph, that will give you the work done. Whenever two quantities, they are getting multiplied. So always the third quantity is given by the area. If suppose the two quantities are getting divided, then you calculate the other quantity using their slope, tan theta. The way if it's x versus t graph, that is displacement versus time graphs, then we don't know x divided by t, that gives us velocity third quantity, which is by slope of it. So since here it is force multiplied by displacement, not force divided by displacement, that's why we calculate the area under the graph. So area above the displacement axis, you write it as positive. Whatever is there below it, you write it as negative. And questions are there from the graphical method. Trapezium, triangle, rectangular, basic figures will be given in the graph. You have to find out the work done, multiply, and get your result. Just note down this part. Just note down area and work done is given by area under the graph, and write area above displacement axis as positive and below is negative. No need to make the figure, just make this part and these two sentences. Done?
Yes, ma'am.
Now see, this concept is used a lot, concept of mechanical energy, because most of the questions you will not be just solely solving it with the help of just the basic formula of work done. You have to have the knowledge of mechanical energy and kinetic energy. Mechanical energy is kinetic energy and potential energy is sum, whatever is the total energy that is present in your system, right? So we are just talking about kinetic and potential energy, but in reality, internal energy also exists, entropy is there, so many energies are present, but currently we'll just focus on kinetic energy and potential energy. See, just one method for kinetic energy, always remember, whenever there is motion of the particle is occurring, then we use kinetic energy. All right, when the velocity is actually getting involved, there is motion of the particle. But in potential energy, it's not necessary just that the particle's position has to change. In potential energy, whatever you have to get it is through the number of interactions. if two bodies interact among themselves. What is meant by interaction? Interaction simply means exertion of force. If two bodies are exerting force on each other, they will be having potential energy. That is just the concept that you have to use to identify kinetic and potential energy. So many questions you have seen where just the application of one single energy doesn't work, one single formula doesn't work. So many times we have to apply the formula and use the concept of energy. So that's why just if you are calculating the number of interactions, you'll get the potential energy. And if you're getting how to use, see, kinetic energy is always, this will always remain a function of temperature or velocity. So just identify these, otherwise their basic formulas remain same. So kinetic energy's formula is half mv square, as you all know. But see, if we convert it in terms of momentum, because momentum is mass into velocity, we get the formula k is equal to p square by 2m. All right, this is the formula for it. K is equal to p square by 2m. Now, work energy theorem basically says that whatever is the change in kinetic energy that has occurred in the body, from first position to second position, whatever change in the kinetic energy that has occurred, work energy theorem is equal to the change in kinetic energy. So whatever above we have studied regarding work done, right now we have just studied regarding kinetic energy. So kinetic energy and work done both are equal. This is what is meant by work energy theorem. So work done is equal to the change in kinetic energy. Whatever is the final kinetic energy minus initial kinetic energy is equal to the work done. This is what is your work energy theorem. So among this, if you have to find out the change in kinetic energy if momentum changes. So see, if momentum changes, it's better if you use this p square by 2m and get it. Whatever is the change in kinetic energy divided by original kinetic energy into 100, this will give you the change in momentum. Use this to find out the momentum's change, and this formula will be sufficient. Do one thing. Just write down this part and write according to work energy theorem, change in kinetic energy is equal to work done. Just write this part and the momentum part, because these are used in your numericals that have come. Now see class, depending upon this angle, we get the type of work done. If the angle is positive, that is, we are getting cos theta is positive. It means work done and the force and the displacement, they are occurring in the same direction. So it will be positive. So in that case, we take cos theta is positive and angle is acute. So work done, this is going to be positive. So positive work done you have. If cos theta is negative, you get negative work done. If you have perpendicular, that is both, either it can happen that force and displacement, they are coming perpendicular to each other. These questions will not come directly as in to solve it, but these will be in your theoretical statement based questions. So work done can be zero, or the work done can be zero if force is zero or displacement is zero. Any of these quantities is zero. Then we have the concept of conservative force. So conservative force basically says that, see, I have this one point is there, this is A point, and this is one more point, that is B point. So I can go by first method also, I can go by the second path also, I can go by the third path as well, right? So forces in which work done is independent of the path, that those forces are known as conservative force. So they do not depend upon the initial and final position. They just depend upon the initial and final position. They do not depend upon whether it is second, first, third, whichever path. So these types of forces we call it as conservative forces, like your electrostatic forces, gravitational forces, all these are conservative forces. If you have a force in nature that depends on the path travels as well as the initial and final point, then we say this is known as what? Non-conservative forces. So you have all the dissipative forces in nature, frictional force, heat, viscous force, all those are known as non-conservative force. So you have conservative force, these are non-conservative force, work done is not equal. Then in potential energy, you don't have to remember one such formula, just remember potential energy is equal to the whatever is the work done. Fine, this is the formula we use for spring constant. So this is also potential, the forces used in whatever is the work done calculated, that is given under potential energy. So just write down this as the heading, spring mass system, right? Change in potential energy is half kx squared. K is the spring constant, x is the displacement from mean position. Quickly write this. See, under conservation of energy, you just have to remember that the mechanical energy is conserved. So whatever is the initial energy, whatever initial energies are there, whether it's potential energy that is acting in the system, kinetic energy is acting, or final kinetic energy is there, potential final energy is there. If any of these quantities is zero, you will directly substitute it as zero. But whenever we apply the concept of conservation of energy, we write all the initial energies equal to all the final energies. So net energy is zero. That is whatever energy was before whatever occur the process, that will be exactly equal to that will occur after the process has over. Just note down this part as well. All right, so this is conservation of energy. So this will be used directly in the formula that we'll see. So here in work done, you have to remember about the formula for it. Power and collision. Power also, let us discuss. Collision I'll discuss with you tomorrow only. See, power, because it's a short topic, power is simply rate of change of work done. So whatever is work done divided by time, that gives you power. So average power is also there, instantaneous power is also there. If you calculating duration from one time to another time, the way we calculate a particular duration is if it is given to you, for example. So in that case, what do? You choose average power, right? But if I give you a very particular time instant where you have to find out the power at that particular instant, right? If I give you calculate the power exactly at 0.0098 seconds, then you have to differentiate it. So dW over dt will be used this at any particular instant. For duration, you just use delta W by T. And again, SI unit for work done is energy. So energy is joule, time is seconds. So joules per second is watt, which we use. Directly we'll be using watt. Now, this is one more relation that we get instantaneous power when force and velocities are given. But when to use this formula? When this force, when you see this force is constant, then only use the formula F is equal to P. Quickly just make headings and just make heading of power and write down this. Then we'll begin with the numericals. Class. This question says that a body of mass 1 kg is thrown upwards with a velocity 20 meter per second. It momentarily comes to rest after attaining a height of 18 meter. How much energy is lost due to air friction? Fine. See, if we apply the conservation of energy, loss of energy will be what? Loss. If we apply conservation of energy, we have to find out the loss in energy. So loss in energy is going to be kinetic energy minus potential energy, right? So kinetic energy is half mv square minus potential energy will be mgh half. What is the mass given? 1 kg. Velocity is 20, so this is going to be 20 into 20 minus mass is 1, g is 10, height is 18. So this becomes 400 by 2, 200 minus 180, which is equal to 20 joules. So option A is correct. Note it down quickly. T class. So it says that a mass m moves in a circle on a smooth horizontal plane with velocity v naught at a radius r naught. The mass is attached to a string which passes through a smooth hole in the plane as shown. So velocity is given, radius is given, mass is given. Now tension in the string is increased gradually, and finally mass m moves in a circle of radius. Now the new radius is r naught by 2. So one thing that is going to remain constant, because you have to find out kinetic energy. So somehow we have to involve quantities which involve kinetic energy themselves. So if we take conservation of angular momentum, whatever is the initial angular momentum is equal to the final angular momentum. So initially mass is m, velocity is v naught, radius is r naught, equal to, finally also mass will not change, that it will still remain m. What will happen to velocity? We do not know, v dash, but radius for sure will become r naught by 2. So r naught, m gets cancelled, v dash becomes 2 times v naught. At least we have this relation with us now. Now you apply kinetic energy. See, final kinetic energy is going to be half m v dash square. So half m, what is v dash? That is 2 v naught whole square. So this is 4 v naught square m by 2. So this becomes 2m v naught square, which is options. Note it down quickly. So see class, as I was discussing with you, that once you have the graph, force versus displacement, you just have to calculate the area under the graph. That will give you the respective work done. So here also work done under the graph will give you. Now see, firstly we have to find out, this is given as 2, this is 7, right? This is 2, this is 7. So here, from here our graph is starting. Look here, from here the graph is starting. This is the exact graph given to us, right? This is the graph that is given to us. So how much is this? See, this is 7, this part is 3. So how much this part will be? 7 minus 3, right? This part will be 7 minus 3, that is 4. And this is already given as 2. So we have the information for the rectangle, that is 2 into 4, right? Then this is the triangle. Again, height is half. Now this separation. This is 12 minus 7. Fine, this separation is 12 minus 7. So half, again, height is 2. So this is going to be plus half into base is 12 minus 7 into height is 2. So this is 8. This is 2 into 4. 2 into 4. This is 8. 8 plus 2, 2 gets cancelled. Half, 10 by 2. So that is 5. So you get 13 joules. So option C. Option C is correct. Quickly write it down. This is a very easy question. All of you try this question. Send me whatever answers you're getting in the chat column. So yes, Hanifa and Saif have answered correctly. It's C option. See, how do we calculate this? Ln is also correct. For total energy, if we write the total initial energy, so that is going to be half m1 u1 square plus half m2 u2 square. Right? Now, let's say, because since we haven't done collision, that's why this is a bit part of collision. This collision, one part, after collision, one particle absorbs energy E. But see, we'll just use the simple concept of conservation of energy. Energy E has been absorbed. This is after collision. So total final energy, this will be half m1 v1 square plus half m2 v2 square plus this additional E energy that we have received, that the body has received. Now for conservation, total initial would be equal to total final. So we'll equate these. That is half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square plus E. Just arrange the terms, bring all the u terms together. Just bring this E is towards this side. So half m1 u1 square plus half m2 u2 square minus E is half m1 v1 square plus half m2 v2 square. This matches correctly with this option, that is C. So C option is right. Just note it down, those who haven't. See, it says that 300 joules of work is done in sliding a 2 kg block up an inclined plane. Height is 10 meters. So acceleration due to gravity, this is 10 meter per second square. So work done against the friction we have to find out. Now see, when net work done, when it is calculated to slide a body up, let's say height is, this is given 10 meter, let's say h is the height right now. We'll put the value 10. So what all do we have to include? For the net work done, we have to include that work done against gravitational force plus whatever is the work done against overcoming the frictional force, because it's an inclined plane, right? Block is there, so frictional force will also come in opposite direction to the motion. So against the frictional force. So total work done, this is given as 300. Work done is work done by gravitational plus work done by frictional. So total work done is given as 300 joules. Now work done by gravitation we have to find out. This is mgh. 2 into 10 into height is also 10, that is 200 joules. This is just because of it. So again, the worst work done against friction, we can get it. This is C. This is 300. This is 200. We just have to find out. This is unknown. This is going to be 100 directly. Work done by friction is work done by gravitation. That is 300 minus 200, which is 100 joules. So which option? B. Note this as well. this says that a block of mass 10 kg moving in x direction with a constant speed of 10 meter per second is subjected to a retarding force F is equal to 0.1 x joules per meter. Fine. This is the force given, distance is given 20 to 30, and final kinetic energies. So just now we had studied work energy theorem. We are going to apply work energy theorem only. Work energy theorem says what? Whatever is the work done is equal to the change in kinetic energy. Now, final kinetic energy minus initial kinetic energy is equal to the work done. But here, final kinetic energy is only asked, that is work done plus initial kinetic energy, right? Now, what is the work done? Work done is fx dx integration. This is the formula. F dot x, you write it for the constant one. For variable, we write it fx dx. We just integrate it from x1 to x2 plus half mv square. Right? Now see, put in the values. 0.1 x dx is given to you. Values are 20. How much is just given? 20 to 30 and subjected to a retarding force. So we have to put a negative sign as well. 20 to 30 plus half, mass is 10, speed is also 10. So 10 square, half mv square. Now see, just integrate this part, minus 0.1 will be constant. X square by 2, limits 20 to 30 plus this is 1000 by 2. So this becomes 0.1 by 2, so 0.05. First, we put the value of upper limit 30 square minus lower limit 20 square plus 500. So this becomes 30 square, and that is 900 minus 400 plus 500 equal to, this is minus 25, this is plus 500. So 500 minus 25, 475 joules. So option 475, A option is correct. Note it quickly. Okay, class, this question says that the potential energy of a particle in a force field, this potential energy is given by A by R square minus B by R, and A and B both are constants. R is the distance of the particle from the center of the field. So for stable equilibrium, see, for stable equilibrium, always remember, for stable equilibrium, just remember this condition. This difference potential gradient is equal to 0. Just remember, this is a condition for stable. Now, how this condition has come, the derivation of it and all this, that is not important to you. You just have to remember the formula. Now, just differentiate, do du by dr. So you have to differentiate A by R square minus dB by R dr. So it's better, instead of writing this in the denominator, we write it in the numerator. Just change the power. So this is going to be A r to the power minus 2 minus B r to the power minus 1. And we have to differentiate it with respect to dr. So minus 2 is a power that will come. A is already a constant. R. Now minus 2 minus 1. That will become minus 3. Similarly, minus sign was already there. Again, we have this minus 1. B is constant. And R minus 1 into minus 1. The minus 1 minus 1. That becomes minus 2. So what do we have? This becomes minus 2a by r cube. This becomes plus b by r square. So this term is equal to 0. So equate it, 2a by r cube. Just bring this on the other side, no? So 2a by r cube is equal to b by r square. So r cube, r square gets cancelled. And we have to find out r. R is equal to 2a by b. So from option 2a by b, this is b option. Okay, class, quickly note it down. Yes, class. All those who have written, you can leave. Tomorrow we'll complete the rest of the part that is left, including collision. All right, class. Thank you so much.